Hello students, how are you? I am Dr. S. Suresh, Assistant Professor in Physics, Vignans Nirula Institute of Technology and Science for Women, Guntur. In previous class, we derived electronic polarizability, that was about electron clouds shifting within atoms. Today, we will study a different mechanism. What happens when the ions themselves shift in ionic crystals like sodium chloride? This is ionic polarization. Today we will discuss about and we will derive ionic polarizability value, and we will also derive ionic polarization in dielectric materials. Let us begin. In ionic crystals like sodium chloride, the crystal is made up of positive ions, that is Na plus ions, and negative ions, chloride ions. In the absence of electric field, these ions are arranged symmetrically and the net dipole momentum is zero. Like this, here I am drawing this sodium crystal chloride diagram without any electric field, sodium ion, chloride ion, this is sodium ion. Like this, symmetrically placed in crystal system, sodium ion crystal. Like this is without any electric field, E value is 0, randomly placed in crystal. Here the polarization value Pi is 0. If you apply an electric field E, what happens? Here sodium ions will move to one place, that is along direction of electric field. These chloride ions move one direction opposite to the electric field. This is called ionic polarization. Here the derivation of alpha I we will derive now. Positive ion displaces by x1 in the direction of electric field E. The restoring force on it is likely the spring force, that is the force acting on the positive ion is E into capital E, whereas E is charge of ion, the charge of electron. Capital E is applied electric field. Here what happens when the electric field applied? For suppose this is a sodium ion will move to x1 distance, and the chloride ion will move other side with x2 distance. That is the total displacement of these two ions is x equal to x1 plus x2. Here this force F is equal to E capital E. In the spring force, the formula for spring force is capital M omega naught square into x1. Here capital M is mass of positive ion. x1 is displacement of ion. Omega naught is angular frequency of crystal system. This is equation 1, that is the force acting on the positive ion due to electric field. Similarly, the force acting on ion, chloride ion, that is negative ion, that is also F. The same force is acting on chloride ion also, that is equal to E into capital E. Here this value is equal to small m omega naught square x2. This is equation number 2. Here the small m, here mass of negative ion, x2 is displacement of ion opposite to the electric field. Here same, the omega naught is angular frequency of the crystal system. The total displacement, now you calculate the total displacement of the ions. Here the total displacement, here x equal to x1 plus x2, whereas x1 equal to, from equation 1 we will get E into capital E divided by capital M omega naught square, and x2 is equal to E into capital E divided by small m into omega naught square. Place these values in above equation, then we will get total displacement value, that is x equal to E capital E divided by capital M omega naught square plus E capital E divided by small m omega naught square. Here we will take common E capital E by omega naught square, then we will get 1 by capital M plus 1 by small m. This is x value is equal to E capital E divided by omega naught square 1 by capital M plus 1 by small m. This is total displacement of the ions. This is equation number 3. Now we will calculate dipole moment, that is dipole moment mu I value. Here mu I is equal to E into x, charge into displacement, that equal to Here from equation 3 we know that x value, that is E into E square E, that is E square capital E divided by omega naught square 1 by capital M plus 1 by small m. This is question number 4. This is dipole moment of the ions. Next we find the ionic polarizability, that is alpha I. Here the relation between dipole moment and ionic polarizability we already know, that is mu I is equal to alpha I into E. That implies alpha I, ionic polarizability, is equal to mu I divided by E. Then we will get alpha I is equal to mu I, we already know. We will get ionic polarizability value E square divided by omega naught square into 1 by capital M plus 1 by small m. This is equation number 5. This is ionic polarizability value. Here E is the charge of the ion, omega naught is angular frequency of crystal system, capital M is the mass of positive ion, small m is the mass of the negative ion. Next we have to calculate total ionic polarizability. Pi equal to, we already know formula, Pi equal to N alpha I into E, that equal to N into alpha I, we already know, that is E square divided by omega naught square 1 by capital M plus 1 by small m into E. This is total ionic polarizability value. Key properties: it occurs only in ionic crystals like sodium chloride, potassium chloride, manganese oxide, not in covalent solids. It is slower than electronic polarization. It is responsive time is 10 power minus 13 second. It is typically smaller than electronic polarization. It occurs and operates up to infrared frequencies, that is it will appears up to infrared frequencies, that is 10 power minus 13 Hz. Lower frequency to 10 power 13 Hz we will see the ionic polarization in the materials. It is not dependent on temperature. This is all about ionic polarization and ionic polarizability. In next video we will discuss about orientational polarization and also space charge polarization. Thank you everyone.